Okay, so this is practice exam midterm 2. This is the second part. And let's get started with question 11. It says, which of the following molecular classes may have a linear shape? Let's go through these pretty quickly here. If we look at the first one, we have AX2E3. Remember that X represents an element and E represents a lone pair. And so we have 4 regions of electron density. They're going to want to get as far away from each other as possible. And so the electron geometry here will be tetrahedral because I'll have my 4 groups or my 4 regions of electron density as far away from each other as possible. However, my shape only considers bonds, and so the shape here will be bent, and so that's not going to work. If we look at the second one, AX2E3, I've got 5 regions of electron density, and when I have 5 regions of electron density, that means that my electron geometry will be trigonal bipyramidal. But you see that we have 3 lone pairs. And so when I have 3 lone pairs, all of those lone pairs are going to be at the equatorial positions like that. And so my molecule in this case will be linear. And so that is the correct answer. Let's take a look at the next one. I have AX4E2. I have 6 regions of electron density. And so that will adopt an octahedral electron geometry, but my molecular geometry will be square pyramidal. And you might be wondering, well, why is it square pyramidal? Well, let's draw it out here. I'm going to have 4 atoms in the plane and 1 lone pair above and 1 lone pair below, like this. And so this is square. So this one would be square, planar, like that. The next one, AX2E, I have 3 regions of electron density. I'm going to have my central atom. They're going to get as far away from each other as possible, but you see that the molecular geometry in this case, which considers only the bonds, would be bent. And then the last one, which is AX3, it's going to be in the same vein as the last one. I've got 3 regions of electron density, and so my electron geometry would be trigonal planar, but it only considers the bonds. And so when I'm talking about molecular geometry, and so the shape here would be trigonal planar. And so the answer is AX2E3. This is linear molecular geometry. Okay, what is the shape of phosphorus pentachloride? First, let's tally up the total number of valence electrons. Phosphorus has 5 valence electrons. Chlorine is a halogen. It has 7 valence electrons times 5. So I have 7 times 5, which is 35 plus 5. That gives me a total of 40 electrons. My phosphorus is going to be in the center, and I'm going to spread those chlorines as far away from each other as possible. And you might be wondering, well, how did you know to do that right away and not start, fiddling around with it? It's because for every one of these chlorines, I have 3 lone pairs and a bond, right? 3 lone pairs and a bond, that adds up to 8 electrons total. And I have 8 times 5 regions of electron density. That gives me 40 electrons. So there is no there are no lone pairs on the central atom. And so the shape or the molecular geometry of this molecule is trigonal bipyramidal. Question number 13 asks us, what's the shape of the azide anion? What's the shape of an azide anion? First, we'll start by tallying up the total number of valence electrons. Nitrogen comes from group 5A. It has 5 valence electrons, and there's 3 nitrogen, so that's 5 times 3 is 15. I add 1 for the negative charge, right? Don't forget that it's an ion. And so I have 16 valence electrons. Let's start by putting a nitrogen in the center, and we're going to have 2 nitrogens attached to it, obviously. And then we just start, putting lone pairs around. If I go 1, so far I've used up a total of 1, 2, 3, 4 in the bonds, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The problem with these is that the nitrogen in the center is electron deficient. It only has 4 electrons surrounding it. So if I move one of the lone pairs there, now you can see the nitrogen is still electron deficient. It is only surrounded by 6 electrons. And so I'm going to remove another lone pair on the other side. And now if I look at it, my nitrogen in the center, the central nitrogen, is surrounded by 4 bonds. Each bond has 2 electrons, so that's 4 times 2 is a total of 8, so those have an octet. If I look at the nitrogens on the end, they both have 2 lone pairs and 2 bonds. 4 electrons from the lone pairs, 2 bonds, 2 electrons in each, so that's 2 times 2 is 4, 4 plus 4 is 8, and so each nitrogen at the end has an octet. So everybody's got an octet, but where is the negative charge? Well, it's not asking us for the negative charge or to place it. But let's do it. The formal charge of nitrogen here is going to be 5 valence electrons minus 4 sticks in 0 dots, so that's plus 1. The formal charge of both of the nitrogens on the ends are going to be 5 minus 2 sticks and 4 dots. That gives you minus 1. And so I have a charge of negative 1 on each of the nitrogens and plus 1 here. The central nitrogen has 2 regions of electron density, doesn't it? Because a region of electron density can be a single bond, a double bond, a triple bond, a lone pair, or a single electron. And since I have 2 double bonds, it's got 2 regions of electron density. They're going to try to get as far away from each other as possible. My bond angle here is going to be 180 degrees, and the shape of the azide anion will be linear. Question 14. What is the shape of tellurium OF5 minus? First, we'll tally up all of the electrons. Tellurium is in group 6A, and so it has 6 valence electrons. Oxygen is in group 6. It's got 6 valence electrons. Fluorine is in group 7A. It's got 7 valence electrons, and there's 5 of those. So that's 35 plus 12 plus 1 for the negative charge, and that gives me a total of 48 electrons. Now, there is a rule that you should be aware of for fluorine, and that is fluorine only ever has a single bond and 3 lone pairs. So we're going to be able to take on, what, 5 times 8? We're going to get rid of 40 of the electrons just with single bonds to fluorine. Now, remember also that the least electronegative element is placed in the center. So we're going to put our tellurium here. We've got 6 regions of electron density, don't we? We've got 5 fluorines and 1 oxygen. So let's start placing those around like this so that our molecular geometry will be octahedral like this. I'm going to put in all my lone pairs like that. Okay. Now, so far, I've used up 8 times 5. That's 40. And then I've got 2 more electrons here. That's 42. I've got 6 electrons to go, and I have a negative charge. Hopefully by now you've practiced enough that you know that an oxygen, when it has 1 bond and 3 lone pairs, it has a negative charge. Let me prove it to you. Oxygen is in group 6A. Subtract 1 stick and 6 dots gives you negative 1. There we go. And so we've got 6 regions of electron density, and so our shape of our ion is going to be octahedral. Question 15. What condition is sufficient to guarantee that a trigonal planar molecule possesses a molecular dipole? If I have a trigonal planar molecule and all of the outer atoms are identical, okay, this is not going to have a dipole, right? No dipole. So let's take a look at what the possible answers are. It says it must contain 3 or more different elements. Right away, I'm seeing something that looks reasonable to me, because in this case, I would have my central atom, and if I had at least 3 different elements, in that case, I would have a dipole, because the dipoles are not going to be balanced out perfectly. So that's definitely going to be the right answer. If you look at the other answers, it must come from the AX2E3 molecular class. I don't know what that would have to do with the trigonal planar, because that would be a linear geometry. It must contain only 1 kind of element. Well, that's not true either. That wouldn't be polar if it could exist. It must contain 2 elements with different electronegativity values. Again, in this scenario here, I've got 2 elements, and if they have 2 different electronegativity values, no big deal, right? Because if I had 3 dipoles going, let's say, all this way, they're going to cancel each other out. And then it says it must contain a multiple bond. Well, that's not necessarily true either. And so the answer is A. Let's look at number 16. You can see that I've gone ahead and put in the molecular orbital diagram here for this one to kind of help myself out. And it's asking us what is the electron configuration of the O2 2- anion. And the first question we want to ask ourselves is how many electrons are in the O2 2- anion? Well, oxygen, who could tell me how many electrons oxygen possesses total? How many total electrons does oxygen possess? Not a trick question. How many electrons for an oxygen? Anybody? No, it's not 6. It's 8, right? Oxygen has a total of 8 electrons, right? It's element number 8. So we've got 8 times 2 plus 2. So that gives me a total of 18 electrons for the O2- ion. I've put up the molecular orbital diagram for oxygen to neon. You will be provided this. It's on the sheet that you are allowed to bring into the examination room. You have to show it to me at the beginning. You just have to show it to me at the beginning of the exam. So 18 electrons. Let's start by putting them in. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember Hunt's rule. 13, 14, 15, 16, 17, 18, like that. And so I neglected to put my 2 here, but these are 2 pi, 2 pi, like this. One of the first things that you could do, in fact, in this question, is that you could just look at the total number of electrons and tally them up, right? If you look at this one here, you see we have 2 plus 2 is 4, 5, 6, 7, 8, 9, 10, 14, 18. So the first one is a contender, right? So that's a possibility. It's got 18 electrons. If you look at the second one, you got 2, 4, 6, 8, 12, 14. So this one cannot be a contender. If you look at the next one, 2, 4, 6, 8, 10, 12. Also cannot be a contender. Look at the last one, 2, 4, 6, 8. Definitely not a contender. And then if we look at the second to last one, 2, 4, 6, 8, 12, 13, 14, 15, 16. And so this one is also a contender because it's got 18 electrons. Now let's look at the first one. We've got sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, pi 2p4. So that would be these ones here. And there we go. So this would be the correct answer. All right, so the correct answer is A. And remember, I just read them off of the molecular orbital diagram in order of increasing energy. Nothing more than that. Let's take a look at this next one here. I can teach you sort of a cheater method for this one. It asks us what is the bond order for neon. Whenever you're dealing with a noble gas, so neon is a noble gas, noble gas. For a noble gas, the bond order is always going to be 0. Okay, but anyhow, I digress. Let's do it anyway. Neon has a total of how many electrons? Well, neon has a total of 10 electrons. So we have 10 times 2, which gives us 20 electrons total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Bond order is calculated as this: 1/2 times the number of bonding orbitals, electrons in bonding orbitals, minus anti-bonding molecular orbitals. Put it like that. So I've got 1/2 times. Let's count up all the electrons in bonding molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 in anti-bonding. Let's count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 minus 10, which is 0 times 1/2, and the bond order is equal to 0. So the final answer is 0, like that. Okay, let's look at question number 18, more of the same. Which one of the following species is expected to be paramagnetic? Well, a student asked me, are we not looking exclusively at valence electrons? You can do whatever you want. You can look at just the valence electrons, or you can look at all of the electrons. When we're talking about electron configuration, which we were a couple of problems ago, in that case, it gave us the 1s electrons in the molecular orbital diagram. And so we wanted to include those. Here it's just asking us which species is paramagnetic. What does paramagnetic mean? Paramagnetic means that it's going to have unpaired electrons and that it will be attracted to a magnetic field slightly. Let's start with the C2, 2+ ion. Now the total number of electrons that carbon has is 6. So we have 6 times 2, which is 12. And then we're going to subtract 2, right? So we're going to have a total of 10 electrons. Subtract 2 because I've got a 2 positive charge. So that's 10 electrons. I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see that the C2, 2+ ion has 2 unpaired electrons. And since it has unpaired electrons, therefore it must be paramagnetic. Okay, and so the correct answer is the first one. Okay, let me just show you with another one just to prove it to you that another one of these choices is not the right choice. So I'll delete this spinach for now. Here we go. Let me delete that and delete that. Let's just try the O2, 2+, and I'll show you that all of the electrons will be paired up. So oxygen has a total of 8 electrons. So 8 times 2 is 16. 16 subtract 2 is equal to 14 electrons. So we would have, let me erase all these ones. There we go. We'd have 14. Let's fill it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So again, you see that everything here is paired up. And so this would be diamagnetic. It is going to actually not be attracted to a magnetic field. Rather, it will be repelled slightly. And in the interest of time, you can do the same thing for all of these monatomic ions. And you will see that no matter what, you end up with everything else being paired up. And so the answer is the first one. Let's move on to question 19. It says, which of the following molecular electron configurations represents an excited state of N2? Now, if we were going to look at just the valence electrons, right, if we were looking at N2, how many valence electrons does nitrogen have? Well, nitrogen has 5 valence electrons, right? So 5 times 2 would give us 10 electrons, but that would be for valence electrons only. You can see that everything here starts with 1s, so we have to include the core electrons. How many total electrons does nitrogen have? It has a total of 7. 7 times 2 gives me 14, and that's for total. Again, we have to include these 2 molecular orbitals because they're included in the electron configurations that are given as possible answers. So let's fill in our 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. One I have drawn here. This is called the ground state. Okay? When it says an excited state means that one of these electrons that's in here has been put into a higher molecular orbital. Okay? Now, the first thing we could do with all of these is just tally up the total number of electrons. That would probably be the easiest thing to do. If we look at the first one, we've got 1, 2, 4, 6, 8, 12, 14. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we've got 15 here. So that doesn't look reasonable. The next one we have 2, 4, 6, 7. 7 plus 4 is 11, 12, 13, 14. So we've got 14 electrons here. This looks like a possible contender. Is it? Let's check it out. We've got our 1s2. That's here. We've got our sigma star 1s2. We've got our sigma 2s2. We've got a sigma star 2s2. We've got a pi 2p4. That's all of these ones here. And then we've got sorry, I misread. I meant this one here is a sigma star 2s1. So that means they took this electron out. Okay, I just removed it from the sigma. No, I took it from the wrong one, didn't I? The sigma star 2s. Sorry, Mr. Dion needs a new prescription really bad, but he has been neglectful in going to the optometrist. I was supposed to do it like 6 months ago. Where am I? Complaining to my students. Shouldn't be doing that. Then we get a sigma 2p2, and then we have a sigma star 2p1. So that means that I've moved one of those electrons into here, and that's the excited state. So we move the electron from here up into here. And so this would be the correct answer, is this one here. Okay, correct answer. If you look at the other ones, I mean, you can see the major problems here. You got 2, 4, 6, 8, 12, 13, 14. So you have 14 here, but you don't have anything that's excited. And here, and this one you get 2, 4, 6, 8, 12, 13, 14. So you have way too many here. And then here you got 2, 4, 6, 8, 12, 14, 16, 18. Okay, so these ones are not possible. So it becomes a battle between, these two here. But you can see that this one at the bottom is the ground state. Ground state. And this one here is the excited states. Excited state. All right, there we go. Well, let's move on to question 20. What is meant by sigma star? What does that even mean? Okay, well, hopefully by now you've learned that sigma star represents an antibonding molecular orbital, which is the result of the addition of two waves that are out of phase with each other. Okay, so it's two waves that are out of phase, and so the possible answers are an antibonding orbital formed from the addition of two 1s orbitals, an antibonding orbital formed from the subtraction of two 1s orbitals, a bonding molecular orbital, no, a bonding molecular orbital, no, an atomic orbital, no. And so the answer is this one here. It's an antibonding molecular orbital that's formed from the subtraction of two 1s orbitals, or the same thing as adding two waves that are out of phase. All right, there we go. Okay, question 21. We're kind of switching gears here and looking at reactions. So this is more content from chapter 4. Chapter 4. Sorry, I had made some notes here and I can't find them. Oh well, if I can't find them, they must not have been very important, could they have been? Huh? All right, well, let's just tackle this one. Question 21. Which of the following chemical equations correctly shows the combination of iron with oxygen to form iron 3 oxide? Well, this kind of is where you get to exercise your nomenclature prowess a little bit. We know that iron is found in the periodic table. Its symbol is Fe. It's a solid. Oxygen is a diatomic element. It's a gas. So we're going to take iron and we're going to combine it with oxygen, which is a gas, and we're going to form iron 3 oxide. You should know that an oxide is O2 minus. Iron 3 means iron with a 3 plus charge. How do we combine those? We get Fe2O3, and that is also a solid. If you look at the possible answers, this is definitely not right because I is the symbol for iodine. Another thing I've noticed is that my equation isn't balanced. And so if I want to balance this guy, I've got to have 2 irons, and then I'm going to have 3/2 here, and I want to get rid of that fraction in front of my oxygen. So I multiply the whole thing by 2, and I end up with this equation, which is 4 iron plus 3 oxygen gives me 2 iron 3 oxide, like that. So that's the correct answer, which is this one right here. Yeah, this is iron 2 oxide. Yep. So there we go. I think this is one of those questions where the best thing to do would be to just solve it yourself and then look for the correct answer. All right, another question that involves a reaction. Number 22, which of the following chemical equations correctly shows the combination of calcium oxide and carbon dioxide to form calcium carbonate? Again, exercise your nomenclature skills. Calcium oxide formed from a metal and a non-metal. will be calcium oxide. If it's ionic, it's going to be a solid at room temperature. Hopefully by now you know that CO2 is a greenhouse gas. It's CO2 gas and calcium carbonate. Well, calcium comes from group 2A, so it's going to have a 2+ charge, and carbonate is CO3 2-. They're going to combine in a 1-to-1 ratio to form calcium carbonate, which is a solid. It's ionic, right? It's formed from a metal and a polyatomic ion that is made up of nonmetals. So let's write this down. Now we've got what? We've got calcium oxide, which is a solid, plus carbon dioxide, which is a gas, produces calcium carbonate, which is a solid. It's not balanced, or no, is it balanced? We've got calcium, one calcium, 3 oxygens, and 1 carbon. There we go, perfectly balanced. And so now we look for that in here, and I'm looking, and it's the first one right there. So there's our answer. Okay, question 23. Which of the following is phosphorus acid? Okay, well, phosphoric acid, hopefully you know that H3PO4 is phosphoric acid, right? Because PO4 3- is 8, right? The suffix is 8. If I have PO3 3-, the suffix is ite, and then when I have H3PO3, I go from ic, right? So from 8, you get an us acid, and when you have an ite, pardon my language, you have ic acid, and when you have an ite, you have us acid. Okay, so we have H3PO3, which is phosphorus acid, like that. Okay, so that's H3PO3. Who can answer? What are the transition metals that have only a +1 charge, or have only 1 charge? They are silver, zinc, and cadmium. Okay, so write those down. All right, silver, zinc, and cadmium. Okay, what is the formula for hydroiodic acid? Well, we looked at the diatomic acids earlier on, and when we have hydrogen combined with another element, we have hydroic acid in the diatomic acids. And so since we have an iodine, iodic acid, it's going to be HI, aqueous, like that. Just a little nomenclature practice. Okay. There's only 2 other acids in here that you should be able to name, which is, so if you have HiO4, that's periodic acid. And then if you have HiO3, that's iodic acid. And then if you have HiO2, that's iodous acid. And if you have this one, it's hypoiodous acid. So just to keep those ones in mind. Okay, question 25 just asks, which of the following represents a decomp reaction, a decomposition? This is where we have, A and B together in the same compound, and they decompose to give us A plus B. So we're starting with less, and we're ending up with more. The first one is some kind of combination reaction, so that's not a possibility. So we could even write that in here. So this is a combination reaction. The next one is a double displacement. You see that the cations and the anions are switching places. So this is double displacement reaction. The next one is just showing the ionization of sodium sulfite into its ion. So this is just ionization. This isn't a reaction. The next one shows calcium carbonate decomposing to give us calcium oxide and carbon dioxide. So this is a decomposition reaction, and that is in fact the correct answer. And the next one is also a combination reaction where we're adding sodium oxide and sulfur dioxide to make sodium sulfite. So this is also a combination reaction. So there we go. We identified the decomposition reaction. The next one, which one shows a double replacement, or sometimes I call it a double reaction? Well, I already answered this kind of in the last one. Which of the following equations represents a double replacement? This is where the anions and the cations swap places. And so if we look at the first one, you see that the silver is combining with the chloride and that the sodium is combining with the nitrate like this. And so this is, in fact, the double replacement. We also call these metathesis reactions. And so this one is the correct answer. If we take a look at the others, the second one is a combination reaction. We're combining sodium oxide and water to make sodium hydroxide. The next one is also a combination reaction where we're combining sodium, carbon, hydrogen, and oxygen to form sodium carbonate in water. The next one is a single displacement, right? Because the aluminum is displacing the copper, but it's only one displacement or one replacement. So this is a single, we'll call it a single replacement. And then the last one is just showing two ions coming together to form a solid. And so that is not a double replacement reaction. Number 27, what is the expected observation when a solution of nickel 2 iodide is combined with a solution of sodium sulfide? Again, more nomenclature. So nickel 2 iodide, that tells us that our nickel has a 2+ charge. Iodide is always -1, so that means you're going to have NiI2. It tells us it's a solution, so that means it's aqueous. And a solution, that means it's aqueous, of sodium sulfide. Sodium has a +1 charge. Sulfide has a 2- charge, so that means that you're going to get Na2S, aqueous. So that means we've got two solutions, and let's write them down. Nickel iodide, 2 iodide, I should say, aqueous, plus sodium sulfide, aqueous. Okay, and what's going to happen? Well, remember, these are aqueous, right? So that means we're going to have a solution that's got nickel ions, iodide ions, sodium ions, and sulfide ions all in the same reaction flask. And some of those sodium ions are going to see iodide ions, aren't they? And they're going to form sodium iodide. Some of those nickel ions are going to see sulfur ions, and they're going to combine to form nickel 2 sulfide, Ni2S. Now, to determine whether there's going to be a reaction or not, you have to go to the solubility table. Now, I asked you to memorize the first two rules, but if you look at the rules for sulfides, it's rule number 6. It says many sulfides are insoluble. And then it gives you the exceptions. Nickel is not one of the exceptions. And so this is going to be a solid. And so you end up with a precipitate in this reaction, and the precipitate is nickel 2 sulfide. Here's the answer. A precipitate composed of nickel 2 sulfide will form. Look at the other possibilities. Nothing. There's no reaction. That's not going to happen. Sodium iodide is not a precipitate. Sodium iodide is a soluble compound. I determined that from the solubility rules. Hydrogen gas, no. A precipitate composed of both of these, no. And so the answer is A. Question 28. What are the spectator ions in a reaction of barium chloride and ammonium carbonate? Remember, the spectator ions are just the ones that just kind of sit around and watch, right? They don't really do anything. So we have barium chloride, which is an ionic compound, BaCl2. We know that it's a soluble compound from the solubility rules. And ammonium carbonate, which is also a soluble compound. What's going to happen when what are the spectator ions rather when we combine those? So let's write it all out. We have barium chloride plus ammonium carbonate. Those are both aqueous. We're going to do a double displacement or double replacement where barium is going to combine with carbonate and ammonium is going to combine with chloride. So barium is 2+, right? Barium is 2+. Chloride is -1. Ammonium is +1. And carbonate is 2-. That means that barium is going to come together with carbonate to give me BaCO3. If I go to my solubility table, and I have mine printed out here, if I look up carbonates, it says most carbonates are insoluble. And it doesn't give us any exceptions on there. So we can take for from the solubility table that we end up with a solid. And we end up with ammonium chloride. And ammonium chloride, if I look it up in the solubility rules, it is a soluble compound. So let's write out all of the ions now. We've got barium, 2 plus, aqueous, plus 2 chlorides, aqueous, plus ammonium, plus 1, which is aqueous, plus carbonate, which is aqueous. And that forms barium carbonate, which is a solid, plus ammonium ion, which is aqueous, plus carbonate, 2 minus, which is aqueous. What's the same? Ammonium. Did I miss my chloride? I did. Mr. Dion's writing too fast. Instead of carbonate, jeepers, dude. Sorry, you guys. Instead of carbonate, or instead of chloride, I put carbonate, didn't I? That wasn't right, was it? Okay, so you can see here that our chloride rather is going to cancel out in my unbalanced reaction, so I can fix this. There we go. BaCl2. What's going on? Oh, I see. I made a mistake, you guys. Nobody called me out on it. It's supposed to be NH4 2CO3, so this is supposed to be 2 ammoniums, like that. There we go. Oopsie doodle. Mr. Dion made a big boo-boo, you guys. Look at this. NH4 2 carbonate. Now I'm going to go in the chat here and see if anybody stopped me. Nope. Okay. Anyhow, next time you see me making a mistake that bad, okay, if I'm working really quickly, just unmute your mic even and just yell at me, and I'll stop what I'm doing. Okay, where was I? I need to balance this out, so I've got 2 chlorides here. Okay, so what's the same on both sides? The 2 ammonium ions. I should balance that out. And what else? Our 2 chlorides, right? There we go. And so the spectator ions are, in fact, chloride and ammonium. So ammonium and chloride are the spectator ions. No, barium carbonate's a solid. Okay, sorry about that one. Anyhow, question 29. Let's see here. Which choice completes the following neutralization reaction, right? What's a neutralization reaction? That's when you add an acid plus a base, isn't it? Okay. We have perchloric acid. This is our acid. We have magnesium hydroxide. That's our base. What's going to happen when we add a hydroxide base to an acid? We're going to end up with water, aren't we? So one of our products is going to be H2O, and the other product is going to be formed from magnesium and the perchlorate ion. We know that magnesium is from group 2A. It has a charge of 2 plus, and perchlorate is HCl4 minus 1. How are they going to come together? I'm going to have magnesium and 2 perchlorates, won't I? There we go. And so if we look at the possible answers, and my reaction isn't balanced, is it? Which choice completes it? It's going to be this answer right here, isn't it? Right? Water and magnesium perchlorate. You can see that this one here is kind of a tricky answer, right? You have to know how magnesium perchlorate is going to come together. That perchlorate has a charge of -1, and that magnesium has a charge of +2. All right, so you're going to want to be on your toes in your nomenclature. Let's see here. Question 30 asks us, given the following balanced oxidation reduction reaction, determine which atom is oxidized and by how many electrons per atom. Let's write it a little bit bigger here. We have phosphorus trichloride plus chlorine gas gives us phosphorus pentachloride, which is a solid. In the chlorine gas, who could tell me what the oxidation state of chlorine is in chlorine gas, Cl2? It's not a trick question. Exactly. Thanks, Joel. It's 0. Any element in its pure state has an oxidation state of 0. Chloride in phosphorus trichloride is going to have an oxidation state of -1. And if I have 3 of those, right, I have -1 times 3. That gives me -3 for all of the 3 chlorines. That tells me that my phosphorus is going to have a charge of +3, or sorry, an oxidation number of +3. The same thing applies to phosphorus pentachloride. My chloride has an oxidation state of -1, and I have -1 times 5 now. So that gives me -5. So that tells me that my phosphorus has to be +5. So who's being oxidized? Right? What's oxidation? Oil. Oxidation is losing. And what are you losing? You're losing electrons. Well, if the phosphorus is going from +3 to +5, that means it's losing 2 electrons. So phosphorus is being oxidized, and it's losing oxidized, and it's losing 2 electrons, right? Because to get from +3 to +5, it's got to subtract -2, right? So that means it's got to lose 2 electrons. And so the answer is phosphorus is being oxidized by 3 electrons per atom. Number 31, let's get into some chapter 5 problems. Says, there's a calculator. I'm trying to find one here on my desk. Okay, a sample of oxygen occupies 4.40 milliliters at 1.20 atmospheres. What will the volume of what will be the volume of oxygen if the pressure is reduced to 0.8 atmospheres at constant temperature? You can see that we are given the initial volume is 44.40 milliliters. You can see that we're also given the initial pressure is 1.20 atmospheres, and we are given the final pressure is 0.80 atmospheres. Well, we learned earlier on pressure is inversely proportional to volume. So if our pressure is going down, our volume should increase. And from pressure being inversely proportional to volume, we can derive Boyles Law. Boyles Law, which is P1V1 is equal to P2V2. And what we're going to solve for here is V2. So we should be able to rearrange this formula and get that V2 is equal to P1 times V1 divided by P2. Let's plug in some numbers. Our initial pressure is 1.20 atmospheres. Our initial volume is 44.40 milliliters. And our final pressure is 0.80 atmospheres. And that will give us, let me get it over here, 1.2 times 4.4 divided by 0.8, and we end up with 66.6 milliliters, but we can only have 2 sig figs. Why? Because there's only 2 sig figs in this number that I've highlighted right here. There are 2 sig figs, and so our volume is equal to 67 milliliters when rounded off. Boyles Law. Question 31. Sorry, question 32. Can't count. Let's see here. A snorkeler fills a syringe with 18.6 milliliters of air at the water's surface, where the pressure is 1.00 atmospheres, and dives to an unknown depth. The volume of the air in the syringe at this depth is 12.4 milliliters. If the pressure increases 1 atmosphere for every 10 meters of depth, how deep is the diver? So the first thing we need to do is we need to solve for our pressure, and then we can determine the depth. Okay, so here we're going to use Boyles Law as well, and we're going to solve for P2. So we have P1 V1 is equal to P2 times V2. Our P2 is going to be equal to P1 V1 over V2. Our initial pressure is 1.00 atmospheres. Our initial volume is 18.6 milliliters, and our final volume is 12.4 milliliters. You can see that milliliters cancel out, and I'm left over with my pressure, which is 1 times 18.6 divided by 12.4, and I get 1.5 atmospheres. So the diver went down and the pressure reached 1.5 atmospheres. That means that the increase in pressure, right? If the person started at 1 atmosphere, that means the pressure that was increased is 1.5 subtract 1, which would be 0.5 atmospheres. And we have a conversion factor that every 10 meters of depth, we get an increase of 1 atmosphere. So we're going to get atmospheres canceling out, and we end up with the diver went down 5 meters as the distance, and that's going to be the final answer. Question 33. All right, question 33. A child holds a helium balloon filled with 2.27 liters of helium gas on a 22 degrees Celsius day. This is our temperature. Let's convert it into Kelvin. So 22 plus 273 is 295 Kelvin. Determine the volume of the balloon if she leaves the balloon in a closed vehicle and the temperature of the gas rises to 49 degrees Celsius. So our T2 is going to be equal to 322 Kelvin. For this, we're going to use Charles' law to solve for V2. And we know that V1 over T1 is equal to V2 over T2. We discussed this law in depth, and we said that volume is directly proportional to temperature, right? If the temperature is increasing, the volume of the balloon should increase as well. So we're solving for V2, and we can write that V2 is equal to V1 times T2 over T1. Let's plug in some numbers. Our initial volume is 2.27 liters. Our second temperature, or final temperature, is 322 Kelvin. And our initial temperature is 295 Kelvin. Look at this. Our units of temperature cancel, and we get that our V2 is equal to 2.48 liters. And so the volume did go up. It rose from 2.27 to 2.48 liters. And that is the correct answer. Number 34. A typical bicycle tire inflation CO2 cartridge contains 12 grams of carbon dioxide. So this is our grams of carbon dioxide. It has a volume equal to 10.0 milliliters and can inflate a bicycle tire with an internal volume of 0.914 liters to 92 psi. What gas in the cartridge?